to my classes on fundamentals of electrical engineering. After the fourth module, that is on signal systems, the logical progression should be to control systems, where most of the ideas merge or proceed or progress. So in the control system module, we'll be looking at different sessions, and these sessions are organized along areas like time response analysis, block diagrams, etc. So in this session, let's look at the time response analysis. And in time response analysis, we will be mostly dealing with the transfer functions that we discussed earlier, the characteristic equation, and some of the components that are there in the characteristic equation. So let's move further by going for the first problem. What do we have here? Two transfer functions are cascaded, and this is the combination will give you what is called as the open loop transfer function, and thereafter the from yt feedback is taken and fed back with a negative feedback. Okay, and the feedback component is equal to 1, or you call it as a unity feedback system. So now let's see what ut is explained as the input and yt is explained as the output. Okay? Sometimes the reference is taken, and so we have rt as the input. Okay? The roots of the closed loop characteristic equation of the system given in figure is what? Okay, so we see. So the best way to do this is, of course, to obtain the characteristic equation, which would be the denominator of the overall transfer function. So what is the overall transfer function? It's given by gs divided by 1 plus gshs. So how do you do it? In a very simple manner, directly from whatever is given. You just look at the forward path, the open loop transfer function. Okay, so what do we have there? Just look at the numerator. So we have 15 and 3. So 15 into 3, 45 comes on the numerator. Then we have 1, but 1 is going to be multiplied by the denominator of the two blocks that are there. So we can directly multiply and give it instead of 1. Okay, so we have s square plus 15 and 16s plus 15, and then you have to add to 15 whatever is right now on the numerator, which is equal to 15 to the 45. So 45 plus 15, 60. In a very simple manner, you can find out what is the overall transfer function of gs divided by 1 plus gshs by putting the numerator, by putting the product of all numerators that are there in the open loop transfer function on the numerator of the closed loop transfer function. Okay, and then whatever you get by multiplying the denominators in the open loop transfer function, you place instead of 1. Okay, so here we are having s square plus 16s plus 15. Then add to it whatever was originally whatever is right now in the numerator, which is 45. So we have 60. Okay, so characteristic equation is now s square plus 16s plus 60, which we can now split into 2. We have to look at both 60 and 16. So we see 6 into 10 is 60 and 6 plus 10 is 16. So the two components are, because it's all positive, the poles of the characteristic equation will be given by s plus 6 into s plus 10, which is the factorization of the characteristic equation. And so the two poles are going to be s is equal to minus 6 and s is equal to minus 10 as given by the fourth option or D option. So let's move to the second problem. Similar procedure is what we're going to operate on in this as well. So what we have there, we have now an inner loop of 10 by s, okay, which is now which is having a unity feedback, negative unity feedback. So now that gives us 10 on the numerator divided by s plus 10, because there is nothing on the feedback path. So 10 divided by s plus 10. Because it is minus, we are getting s plus 10. And that is going to be cascaded to 10 by s. So 10 by s into 10 divided by s plus 10. Yeah, now we have another unity feedback coming there. So in total, it's going to be 10 into 10 100 on the numerator divided by s plus 10 into s. That is going to be s square plus 10s. And then you're going to have also and then you're going to have the numerator repeated again as 100. So s square plus 10s plus 100 happens to be the overall transfer function. It's also the same as equal to the output ys divided by the input rs. Okay. Now we have another pattern emerging here. We see that when you're having omega n square or 100 divided by s square plus 10s plus 100, it is the same as equal to omega n square divided by s square plus 2 eta omega ns plus omega n square. So omega n square is 100, omega n is equal to 10. And 2 eta omega n is what is called as 10. Okay. So now let's see what the problem is. The damping ratio and undamped natural frequency of a closed loop system as shown in the figure are denoted as eta and omega n, okay, as we just now mentioned, and we want to find that out. Okay, so omega n is already found out as equal to 10 and 2 eta omega n is 10, so eta is equal to 10 by 20 or 0.5. Okay. So we have option A as the correct answer. Moving on to the third problem, again another open loop transfer function block given by k by s plus 2 with a feedback. It's not a unity feedback. The feedback is given by 1 plus sp, and of course it is negative feedback. So now what we have, the question is the block diagram of a closed loop control system is given by a figure. The values of k and p such that the system has a damping ratio of 0.7. So damping ratio is eta, and then undamped natural frequency omega n of equal to 5 radians per second are respectively equal to. So as usual, we find the overall transfer function. So what's the overall transfer function? We have k on the numerator, and we have s square plus 2s plus again 1 plus sp into k, or k plus ksp. So now we have omega n square as equal to, omega n is given as 5, so omega n square is equal to 25. So we see that this is the same as equal to k, because that's the only constant available in s square plus 2s plus k plus ksp, or 2. Okay, so now we have, so similarly we have also 2 into kp, or 25p is the same as equal to 2 eta omega n, and omega n is equal to 5. So, and we also know that the eta is equal to 0.7. So 2 into 0.7 into 5 is equal to 2 plus 25p. So p can be easily solved as equal to 0.2. So we have, again in this case also, the fourth option is coming out right, that is k is equal to 25, which we obtain from omega n square is equal to 25 as given by the only constant in the denominator of the overall transfer function. And then we also have 2 eta omega n, the same as equal to the coefficient of s, which is equal to 2 plus kp, or k is equal to 25. And so we see that we can easily, and that can be equated to 2 eta omega n, that's equal to 2 into 0.7 into 5. So both the values can be obtained very easily by a simple understanding of the closed loop transfer function given by Cs by Rs in this case, which is the same as equal to Gs divided by 1 plus GSHs. Okay, so now we move on to the fourth problem. What do we have there? Again, we have two blocks. One is in the forward path, the other is in the feedback path. So now we can get the overall transfer function Cs by Rs as equal to k, which is on the numerator as it is, divided by s square plus 2s plus 1 plus as. Okay, so that can be rearranged to obtain k divided by s square plus as coefficient of s 2 plus ka and plus k. Okay, so k is going to be omega n square as may be revealed, and 2 plus ka is going to be 2 eta omega n. A similar problem. For the system shown in figure, the damping ratio eta is equal to 0.7, just as before, and undamped natural frequency omega n of equal to 4 radians per second, the value of k and a. So very simply, you can substitute for omega n square as equal to 4 square or 16, which is equal to k. So k is already obtained, and then 2 plus ka or 2 plus 16a is the same as equal to 2 eta omega n, or 2 into 0.7 into 4. So easily you can find out the value of a as equal to 0.225, and k is already solved as equal to 60. Very simple, repeated kinds of problems. So control system is generally very easy to do, but of course very few formulae needs to be remembered, and you can be quicker if you follow some of the tips that I'm trying to give you. Okay, so let's move on to another problem. The fifth one, a second order real system has the following properties. The damping ratio eta is equal to 0.5, undamped natural frequency omega is equal to 10 radians per second. The steady state value of the output to units input is 1.02. So much of data is given. What is the transfer function? Okay. So transfer function, as we know, the denominator we have the characteristic equation. So we have omega n square or 10 square as the constant in all cases. So all answers are appropriate in that manner. Next is 2 eta omega ns. That is going to be the coefficient of s is going to be 2 eta omega n. So 2 into eta is 2 into 0.51. 1 into 10 is equal to 10s. Okay, so we have two answers, that is B and C, with s square plus 10s plus 100 as the characteristic equation. Now let's look for the k value. So now k value, we see that we are having a steady state value of the output to a unit step input as equal to 1.02. Okay, so we have 100 on the numerator as it is, because k divided by or omega n square divided by s square plus 2 eta omega ns plus omega n square is the pattern that we are following. Moreover, now we are going to have 1.02 also. So 1.02 into 100 is going to be 102, and only B is coming out with such a situation wherein we have k into or omega n square into 1.02, which is the multiplying factor, and then on the denominator s square plus 2 eta omega ns plus omega n square. Okay, so now let's go for the sixth problem. What is that? We are having a set of transfer functions on one side and nature of the system. Okay, so this is another nature which is being revealed by the characteristic equation as such. Okay, so what do the characteristic equations have? We have omega n square as also 2 eta omega ns. Okay, so we can find out the value of eta in all cases, and eta is equal to 1 for critically damped cases. It is going to be greater than 1 for over damped cases and less than 1 for under damped cases. Okay, so what do we look? So we have a good look at P, Q, and R, and we are supposed to match the transfer functions of the second order systems with the nature of the systems given below. So we have all the over damped, critically damped, under damped is given. So the best thing is to see where if you can find out omega n square in any of the cases. So we see that Q has 25 and both on the numerator and the denominator, and so we have 25, that is we have omega n square divided by s square plus 2 eta omega n. In that case, eta is given by 10 divided by 2 into 5 or it's equal to 1. So it's a clear case of critically damped case. So 25 by s square plus 10s, that is Q plus 25 is referring to a critically damped case. Why? Because eta is equal to 1. Okay. Now let's look at s square plus the first one, the s square plus 5s plus 15. Okay, so once we solve and one more, the other one comes out automatically. So we can look at any of them, but it's better to go for what is called as when we are having a small value for eta, the combination of 2 eta omega n. So we have 5 there. So s square plus 5s plus 15, you just rewrite as equal to s plus 2.5 whole square. So we are having s square plus now 5s and the rest. Okay, so we have 2.5 square is 6.25, and so we have the rest as rest from 15 as equal to omega k square. So we have s square plus 5s plus 6.25 plus 8.75. So now we have 8.75 on the denominator, 8.75 as omega k square, and you also have what is called as a constant on the numerator. Okay, so it's a constant. So it's going to give you what is called as a, if you take the Laplace inverse, the whole transfer function is going to give you something like, of course, there might be a constant multiplied by sine omega kt, where omega is already resolved, multiplied by e raised to minus eta minus alpha t, where alpha is the same as equal to 2.5. Okay, so the purpose of resolving s square plus 5s plus 15 as equal to s plus alpha whole square plus omega square was simply to obtain the Laplace inverse as a damped sinusoid. If it's a damped sinusoid, it is oscillatory, so it is under damped. Okay, so we see that 15 divided by s square plus 5s plus 15 is referring to an under damped case. So obviously the next one will be a over damped case. Okay. So you can resolve that as well, but then you'll have to get something like e raised to you'll have to get something with s plus alpha and s plus beta on the denominator, such that you get e raised to minus alpha t plus e raised to minus beta t with coefficients with constant coefficients. So now so we see that Q is critically damped. So Q2 is the solution for in cases A and C, and already saw that P is under damped, so P3 should be 3. So automatically C is going to be the naturally C is going to be the solution. Okay. Now we move to the seventh problem. The transfer function of a system is given as 100 divided by s square plus 20s plus 100. This system is, so we have 100, 20s, okay, and we also have what is called as omega n square as 10 and 2 eta omega n as equal to 20. So in this case, we see that 20 divided by 2 into 10 is giving you an eta value is equal to 1. Also, it is a critically damped system as given by the C option. Okay, moving to the 8th problem. So consider a negative unity feedback system with the forward path transfer function. So for forward path transfer function is given s square plus s plus 1 divided by s square plus 2 s cube plus 2s square plus 2s plus k, where k is a positive real number. The value of k for which the system will have some of its poles on the imaginary axis. Okay? So another aspect is being investigated here. It's a negative unity feedback system. So the characteristic equation can be easily written as equal to, we have the denominator coming over as a multiplication of 1. So we have s cube plus 2s square plus 2s plus k plus s square plus s plus 1. The numerator has to be added. So now the totality is going to be s cube plus 3s square plus 3s plus k plus 1. Okay. So when you see such a structure, it is nice to have what is called as it's nice to take out s square and get s plus 3 from the first two terms, okay, and then take out 3 and get s plus 3 on the other terms, such that when you take out s plus 3, you have s square plus 3. So we automatically will have it. This will give you a structure for what may be called as the poles on the imaginary axis. When you are trying to resolve the characteristic equation, you get a pole at s is equal to minus 3. You get two poles at plus root 3j and minus root 3j, because s square is equal to minus 3. So if you solve for it, you get two poles. One is at root 3j, and the other is going to be at minus root 3j. So they are on the imaginary axis. This is a better way of doing the problem by seeing the structure of the characteristic equation, wherein from the first two terms you can take out s square, such that you get s plus 3. And if k is going to be equal to 8, then 8 plus 1, 9, you can take out 3. And so you have what is called as 3 into s plus 3. So that's the only reason why this is one of the tricks, the trade that you can employ when you're doing gate examinations. Okay, so let's move to the 9th problem. This is the 9th problem. Each of the following options is correct for the system shown below. Okay, as usual, we have what is called as we are going to have 20 on the numerator. Okay, 1 into 1 and also 20. 1 and 1 on the numerator. On the denominator, you are also going to have s plus 20 coming over, because the last term in the denominator will be 20 divided by s plus 20. So now we have, instead of 1 being multiplied by simply s plus 1 and s square, we also going to have s plus 20. So now we have s plus 20, s square and s. So obviously it's a fourth order system, okay, and we are having two answers which are talking about fourth order. Moreover, we have a multiplication by s square coming over. So what happens is that one term in s will be missing. Okay, you don't have to do the entire Rutherford's criterion or anything like that. Just because you are having s square there, of course you are going to have a constant as given by 20, but then you are going to have terms such as s plus 1 multiplied by s square multiplied by s plus 20, because s plus 20 is to go over to the numerator, it has to multiply the quantities s plus 1 into s square also. So now we see that ultimately you will be left with the characteristic equation which will have a term missing of S. If that is the case, then it's going to be an unstable system. Okay, so as simple as that, you don't have to go for the Rutherford criterion directly. Okay. So let's go to another aspect wherein consider a linear time invariant system whose input RT and output YT are related by the following differential equation. So the same transfer function that we have been doing so far is now given as a differential equation of d square y by dt square plus 4yt is equal to 6RT. So ys by rs is the same as equal to 6. Of course, 6 into rs is going to come. So ys by rs is the same as equal to 6 divided by s square plus 4. Okay. So now we have s square plus 4. As was mentioned earlier, we will have two imaginary terms. One is going to be plus 2j and other is going to be minus 2j as the poles of this system. And that's what's asked, the poles of the system. Okay? So plus 2j and minus 2j immediately strikes our mind and eyes and we opt for option A. Okay, so moving to the last problem in this last slide. Which of the following system has maximum peak overshoot due to unit step input? So when a unit step input is given, another important understanding for the system happens to be that it has a peak overshoot. Okay, it's given by e raised to minus pi, and it's called as MP, and it's given by e raised to minus pi eta divided by root of 1 minus eta square. Okay, so here eta, as so long as eta is very small, you're going to have what is called as a larger peak. Why? Because MP is given by 1 by e raised to pi eta divided by root of 1 minus eta square. Okay. So now we see that, so we look for the coefficients of S. 10s, 15s, 5s, 20s. 5s happens to have the smallest coefficient, which will give you what is called as the smallest value of eta, such that when e raised to minus pi eta, e raised to pi eta divided by root of 1 minus eta square comes on the denominator, you are going to have a larger output, a larger overshoot or a maximum peak overshoot. Okay, so that's all this in this session. I hope the 4 different aspects that we talked about are clear to you. One is, of course, the fact that from the given structure you can derive the overall transfer function, and when you have the overall transfer function, you have the characteristic equation at the denominator. Okay? So each will have poles. Okay? And you can also, okay, so another important aspect is that you can have, you can see that a structure is given by omega n square divided by s square plus 2 eta omega n square, omega n plus omega n square will give you both the damping coefficient eta as also the natural frequency of oscillation omega n. Okay? So now we are having 3 different types of systems. Okay, 4 different types. One is, of course, the critically damped, over damped, and under damped. Okay, and then you will also have the oscillatory system wherein you have a pure sinusoid, okay, not a damped sinusoid. Okay. We also have what is called as some of the specifications, like for instance, the maximum overshoot for a unit step input will be given by e raised to minus pi eta by root of 1 minus eta square. So whichever quantity has the lowest value for eta will have a maximum overshoot. Okay, so this is some of the things that we examined, and I repeat that so long as you have the tricks, the control systems happens to be one of the easiest portions to score maximum marks in the GATE examination. So I wish you all the very best, and we'll continue with the next session. Thank you.